So just a little bit of background. Sungas Renewables is an energy company. We are biomass gasification. We are born out of GTI Energy in 2020. We spun out. We have since been in a sort of slow acquisition from C2X, who is a Maersk spin out as well. And what we are intending to do is take this gasification technology from GTI and commercialize it as a platform for biomass gasification throughout the world. To that end, we started working on a small project internally looking at the pilot plant, primarily trying to do the CFD simulation in and around the pilot facility. We had the majority of our data from that sort of facility. We started talking to Peter and the group here at CPFD in around 2023 and getting those parameters put together, getting all the data together for those specific models using the data from the pilot plant. In 2024, he approached us with, from the DOE, this Energy Works program to scale the gasifier up to the commercial scale. And so we found that very intriguing. We worked with his group of people. We won a grant for that and began work on trying to, what it's going to take to scale it up to the System 1000. And so there was a lot of model refinement, effect on the bed properties as they went through all this work. And now we've got to the point where we've got a reasonably good model of what we think that System 1000 looks like. But this talk is just sort of walk us through the process of what we did, how we did this, and what was the purpose of all this work that we put together. So you may want to ask, why were we doing this? GTI has done these sorts of gasification plants for roughly 40 or 50 years. We have a lot of very basic knowledge of how it goes together. There's a lot of correlations from our friends at PSRI, who were part of GTI for the longest time. And it's just, this is technology that within GTI is very well known, and it's been established and it's been proven for many, many times. What it becomes is a de-risking thing. The question that we would always get from financiers is, show me that plant. Show me that 1,000-ton-a-day plant on biomass. Show me that 1,000-ton-a-day plant at 10 bar. We can't do that, but what we have is a lot of data around coal plants at 10 bar. We have a lot of data around coal biomass at smaller scale. So using the work that we did here with CPFD, we're able to then begin building these models so that we can take these to the financial markets, partially as a scientific tool, partially as a marketing tool. They can start to see that what we know inherently about the systems, we can then model and we can validate these models and show that this is true. So it was a data-informed, modeling approach. We were using true operational data from heat mass balances from the work that we did at the pilot facility, and then we'd taken that to the scaling up of the overall full System 1000. Okay, so why does this matter? So biomass gasification is very complex, as we saw with Eric. These are the same types of gases. So, I can say from our system, we're going through here, we're going into the POX system, and we're using an Arvos cooler. So I know very much what's going on between all these sorts of modeling that's happening here. This is the primary gasifier. We're bringing in biomass. It can be highly variable on the chemical componentry side of it. There's a bed material in there that's acting as a big heat sink, bringing it in, heating that biomass up very quickly. A lot of reactions between devolatilization, drying, tar reforming, water gas shift. I mean, we have a dozen or so reactions ourselves, not the 600 reactions that these guys are working on. But we're trying to just sort of do this very simply. We're more concerned about the hydrodynamics, the fluid dynamics of what's going on, but can we get the mixing right that makes things look more or less where they really should be? And so that's where the benefits of the CPFD modeling are, is that we can actually visualize what's going on within the reactor. And does that make sense from what we have seen in the pilot facility and the data that we're getting there versus what we're seeing in the model, and does that all hang together so that we can say that the model is truly validated? So our first step in the pilot scale models, we had all the actual drawings from the construction of the pilot, all the fabrication drawings, so that we could transmit them to CPFD and they could build an actual model to the dimensions of what the pilot facility were, all the way down to where we introduced the gases in between our grid and our jet, and then we could actually simulate these things as close to reality as we possibly could. Once we got there, we started looking at the simulations and try to get an idea of, do these things make sense? Do they make sense versus the data? Do they make sense, from a standpoint of actually operating the pilot facility? Do these things, do they all sort of hang together? And we went through several iterations and looking at the data to calibrate these things, primarily around temperature, but also we do some data reduction of the bed itself and looking at the bed activity. And so this was the foundation for being able to scale up, is that we had a pilot model that was well calibrated. Our kinetics, like I said, were significantly smaller. We were primarily looking at a drying step, a devolatilization step, which is just sort of taking the gases out of the biomass that's there, some steam-carbon reactions, some reforming reactions, and water-gas shift, and maybe some Boudoir reactions. So we tried to keep our data set relatively small, since we're primarily looking at the major gas species, and the tar is more of a gross number. We're not necessarily looking at individual species of tar, but do we have roughly the right amount of tar and the right amount of methane that's coming off of the system? And for us, that's good enough. We'll let our POX guys take care of the rest of that, and reforming everything to the total amount of syngas. So all of this tied together with the first model we took forward into looking at, this is the validation. And so looking at the velocity regimes, gas temperatures, and total solids within the system, and looking at the data, everything looked relatively reasonable as far as hanging together. So we were confident that we were able to go to the scale up from these sorts of works. We did run across a couple of interesting phenomena as we started into the modeling, and you'll see this base case versus this modified case. The base case, we had given CPFD a certain particle size distribution of the bed, and when the results of the model came out, we found it's basically a packed bed at the bottom. That didn't look right from what we had experienced with the pilot facility. When we looked at the particle size distribution we had given them, it was a little heavy on the heavier side of the particles. And when we took a look at the actual pilot data from what came out of the reactor after the reactor had been running for a while, it was significantly different. So we modified the particle size distribution to what in the middle of the reaction period would look like, and not necessarily at the beginning or at the end, but more in the middle. And that's what we have on the modified case over here, is a much more well-fluidized system than what we had originally started out. So that was one of the good learnings from this, is really look at your data, look at what's coming out. Does it match both from the data standpoint and just from what your experience is when you're running the experiments? So this is, particle size distribution. It was highly sensitive to those particle sizes. As we modified them just slightly, we were able to get the better amounts of fluidization. It had a massive impact on the mixing and dispersion, the temperature uniformity, and as we adjusted that particle size to more along the lines of what it was really going to be within the reactor converged into more of what we would expect it to actually operate like. So a little bit about the System 1000. Our biomass gasifier sits there sort of in the center as the centerpiece of it, bringing feedstock in, converting it to gas and a small amount of char. And then you'll see we have the tar reforming syngas cooler, just as Eric had talked about. This is an entire system. The whole purpose of it is to be a fully integrated with subsystems, feedstock flexibility, which helps us with the CFD modeling, helps with that as well. And we're sustainability focused, trying to stay primarily within the realm of biomass and waste. And this modeling and optimization, again, is the whole purpose is to be able to take this and show that not only do we have the pilot data, but we've also done simulations to the point where we're confident that this is going to be able to operate as we expect it to operate. So as we transitioned from the pilot to the full scale, we had to take a look at the overall validation of things. We had to carry forward all the kinetic elements, and we had to take the structure and scale things up. So we had gone through a series of exercises looking at the larger scale unit. We've actually gone through and had fabrication drawings done. So we had a good idea of the dimensionality of the full scale system, and putting together that with the fabrication drawings and then CPFD laying on the grid network on top of the model. And we were working with somewhere near 1 million cells on this thing to model, because it's a fairly large reactor, and to make sure that we've got a good resolution of what was going on within the overall system. So yeah, we incorporated quite a few cells in this thing to get an accuracy of it. The baseline model served as a starting point for the overall system. So we reused all the reaction, the kinetics of the system. The assumptions were consistent. So as we talked about, there was different reaction regimes within this thing: the drying, the devolatilization, and the reforming types of reactions. We kept those relatively consistent as we went through and did the scale-up of the overall system. The reliable scale comparison, again, keeping the geometry the same, keeping the velocities the same, the steam, the carbon ratios, the oxygen that was necessary to go into the system. Again, very similar as we would go through and do our own modeling outside of CFD to do the actual process design of these systems, and it corresponded with what we were doing with CFD. You see here that, again, particle size distribution and both the reaction kinetics that we were working through as we were going up to the larger scale. As we got to the larger scale, we started seeing the action of what we call the jet in the center. We had another presentation about the ebulated, or a spouting bed, similar type of thing here. We do have a jet in the center that promotes a lot of this mixing. With the smaller pilot, you don't necessarily see this because of all the wall effects that are going on with a significantly smaller reactor. On the right-hand side, though, you do start to see this jet, which is then essentially pulling material from the sidewalls into the center area where you get the majority of your oxygen that allows the reactions to occur, and bringing those solids up into the upper freeboard area, where they then cascade back down along the sides. And as the biomass is being brought in from the sides, it helps to sweep that biomass into the center, along with the grid, everything sort of pulling everything to the center, so that we don't trying to avoid the gas bypassing around the outside of the reactor. The other interesting thing as we got into this was looking at what's going on with all of the reaction zones and primarily the jet. The UGAS reactor in its infancy was a slagging reactor, but it was a dry slagging reactor where it was trying to slag the very small particles of coal into like little BBs. The way we're operating the biomass gasifier, we don't want that. We want to try to keep the system as dry as possible. One of the problems that we're going to run into with biomass is the ash fusion temperature can run anywhere from 800 degrees to 2,000 degrees C. We've seen across the entire spectrum. As we look at our jet here, we can see temperatures nearly 2,000 degrees Fahrenheit. So as we get some of these maybe very low temperature melting biomass ashes, we'll have to be very cautious as to how we operate the reactor, that we don't want to cause these types of ashes to slag and cause the reactor to go down. So we find this is a very helpful tool to even show the potential projects that the biomasses that they're getting in, they may have to get a different type of biomass. We may have to run the reactor in a different form to avoid these sorts of hot spots that will cause the ash to potentially slag within the gasifier itself. So we do have a few remaining gaps. We have a lot of smaller areas within the reactor that we need to take a look at. Around the grid, I was just talking with one of our colleagues here at CPFD. They've rearranged the grid holes to match more closely the way that our reactor is going to operate. it's shown some interesting results in there. We need to take a look at these areas around here with the sorry about that, hold on, right. These areas around the shoulders where we swage and go up to a larger diameter, we need to probably take a little bit closer look at those, and do we truly have dead zones there, or are they more active than maybe what we're seeing here on the reactor? As the reactor started up, it looked like it was a relatively light bed. It may have to be more denser than that. And those are the sorts of things, as we start to understand what the outputs of the reactor or the CPFD modeling is telling us and how we think the reactor is going to operate, we'll begin to be able to refine the model and get it closer to what we expect it to be. There's still a few uncertainties in here, making sure that the kinetics, particle transient conditions, things like that, we'll have to continue to investigate those to make sure that that they're being modeled properly. The bed material is always attriting. We're always adding bed material in. We're always taking bed material out. Those sorts of things have not been modeled into here, and that's going to take significantly more effort to get to that sort of level of modeling on this. And so that's kind of how we're taking this thing forward with CPFD, sort of piece by piece at a time, understand what we have, refine what we have, make sure that it's to a point where it's ready to move forward, and then we take it to the next step as we get mature our process here. And so as people go through this modeling step, the best thing that you can do is have good lab data, experimental data that can then go in and inform your actual model, so that you're not having to guess at things, you're not having to go to books, you get something you can actually truly anchor this thing on. Using it for risk reduction, optimization, and to help tell your story is a wonderful thing for these sorts of tools. And what we will find is that there will be a cumulative benefit of this as we get out into the marketplace even farther with these next projects. The investment community and their due diligence teams they'll put a lot of faith in these sorts of models and the fact that we can hang these back to actual data from the pilot facility. That's it.